sklearn, neighbors, KNeighborsRegressor. Description: KNeighborsRegressor is a non-parametric, lazy learning algorithm used for regression tasks in machine learning. It operates based on the principle of k-nearest neighbors, where it predicts the output value for a new data point based on the values of its k-nearest neighbors in the training dataset. Inputs: X. This is the input feature matrix containing the training data. Each row represents a data point, and each column represents a feature. Y. This is the target variable array containing the corresponding output values for each data point in the training set. Outputs: YPRED. This is the array of predicted output values for the given input data. Model: this is the trained KNeighborsRegressor object. It can be used to make predictions on new data points. Steps: Training: the algorithm first learns from the training data by storing all the data points and their corresponding target values in memory. Prediction: when a new data point is given, the algorithm identifies the k-nearest neighbors to the new data point based on a chosen distance metric. It then calculates the predicted output value by averaging the target values of the k-nearest neighbors, weighted by their distance from the new data point. Metrics: mean squared error MSE measures the average squared difference between the predicted and actual target values. Root mean squared error RMSE, the square root of MSE, providing a more interpretable measure of prediction error. R squared R indicates the proportion of variance in the target variable that is explained by K. Model: visualization plots. Scatter plot plots the actual target values versus the predicted values to visualize the model's performance. Residual plot plots the difference between the actual and predicted values residuals against K predicted values to check for patterns or trends. Fine-tune parameters. N neighbors, the number of neighbors to consider during prediction. Higher values can smooth out predictions but may lead to overfitting. Weights specifies how to weigh the contribution of each neighbor. Uniform gives equal weight to all neighbors, while distance weights neighbors by their inverse distance. Metric: the distance metric used to calculate the distance between data points. Common options include Euclidean, Manhattan, and Minkowski. P. the power parameter for the Minkowski metric. P1 corresponds to Manhattan distance, while P2 corresponds to Euclidean distance. Uncertainty methods. Confidence intervals can be calculated for the predictions by considering the spread of K target values among the k-nearest neighbors. Challenges and fixes. Challenge 1: overfitting. The model can overfit to the training data, leading to poor performance on unseen data. Sample use case: using a small value for n neighbors or a complex distance metric may cause overfitting. Fixes: increase n neighbors to smooth out predictions. Use a simpler distance metric, such as Euclidean distance. Employ techniques like cross-validation to assess model performance on unseen data and avoid overfitting. Challenge 2: sensitivity to outliers. The model can be sensitive to outlier data points, which can disproportionately influence the predictions. Sample use case: an outlier data point can be assigned a large weight if distance weighing is used. Fixes: preprocess the data to remove or handle outliers. Use robust distance metrics that are less sensitive to outliers. Consider alternative algorithms like random forest regressor, which are less susceptible to outliers. Challenge 3: curse of dimensionality. The model's performance can degrade as the number of features increases, making it difficult to find truly close neighbors in high-dimensional spaces. Sample use case: with many features, the distance between data points becomes less meaningful. Fixes: Perform feature selection or dimensionality reduction to reduce the number of features. Use different distance metrics that are more suitable for high-dimensional data. Consider alternative algorithms that are better suited for high-dimensional data, such as support vector machines.